In this video, we present a brief classification of different types of ordinary differential equations. So looking at section 12.2, classification of ODEs. So the first parameter that we can classify ODEs by is the order. So the order of an ordinary differential equation is the order of the highest derivative appearing in the equation. So for example, the equation here, which is an application of Newton's equation, is a second order ODE because it has the highest derivative is a second derivative. So the second derivative of position with respect to time gives us the acceleration. Well, the beam equation is a fourth order ODE because the highest order derivative that we have is the fourth derivative. So the fourth derivative of deflection with respect to x appears in this ODE. The next parameter to look at is whether it's linear versus nonlinear. So an ODE is linear if it can be written as this linear combination as shown here. So basically, if all of the terms can be written as a linear combination of AIX, DIY by DXI, as shown here. So where AIX and f of x are functions of the independent variable x. So many of the examples in the previous section, with the exception of the predator-prey model, were examples of linear ODEs. Another parameter to consider is whether it's homogeneous versus non-homogeneous. So homogeneous ODE is an equation where every term contains either the dependent variable or one of its derivatives. So for example, the free vibration of a spring mass system is a linear homogeneous ODE, described by the equation shown here. So m d2x by dt squared plus kx is equal to 0. So if we bring everything that has either an x or the derivative of x onto one side of the equation, we should have 0 on the other side of the equation if it is homogeneous. So if one of the non-zero terms in the ODE contains neither the dependent variable nor any of its derivatives, then the equation is non-homogeneous. So for example, forced vibration of a spring mass system is a linear non-homogeneous ODE. So here you can see that we've got m d2x by dt squared plus kx is equal to f of t. So here we've got something that is not does not have an x in it. So it's not either a function of x or its derivatives, but it can be a function of time and it can be a constant. And this gives us a non-homogeneous ODE. The free term, the one that is devoid of the dependent variables and its derivatives, is called the source term. So in the case of forced vibration, it is typically called the forcing function. So a linear homogeneous ODE has the form as shown here. So again, if we bring all of the terms that are a function of the dependent variable, which in this case is y, and its derivatives onto one side of the equation, then we have a 0 on the other side of the equation in a homogeneous ODE. And a linear non-homogeneous ODE has the form as shown here. So again, if we bring all of the terms that have a y or derivatives of y onto one side of the equation, we still have something left on the other side of the equation. And this something can be a function of x or it can be a constant. And here the term f of x is called the source term. So the solution to a linear homogeneous equation is called the complementary solution, denoted as yc. And when a source term appears in the equation, then the total solution is the sum of both the complementary solution as well as the particular solution, which we can call yp. And the particular solution, the form of it, is particular to the source term f of x. So for example, the solution to the free vibration response with Newton's equations, which is the homogeneous equation, has the form x is equal to c1 cosine pt plus c2 sine pt. And we saw in the previous section how we can relate these c's to the initial conditions x naught and v naught. But here we can just write it in general as some constant times cosine pt plus another constant times sine pt. where P is the natural frequency of the system. If you, for example, have a harmonic forcing function or source function, so f of t is equal to f naught sine omega t, then the total solution has the form shown here. So it's a combination of the homogeneous solution as well as the particular solution. And the particular solution is related to the forcing function or the source function. So in this case, with a harmonic source function, we end up with a harmonic particular solution. So this has sine omega t, this also has sine omega t. And there are lots of other examples of both homogeneous and non-homogeneous ODEs that we can encounter. The other classification that's important is whether it's initial value problem, IVP, versus a boundary value problem, or a BVP. So depending on the boundary conditions, an ODE can be classified as either an initial value problem or a boundary value problem. An initial value problem is when an ODE is given with initial conditions of the dependent variable and its derivatives at a particular value of the independent variable. So this usually applies to dynamic systems whose independent variable is time. So for example, the examples that we discussed with Newton's second law of motion are initial value problems where we specify the initial value at t is equal to 0 of the displacement, so x at 0, and the velocity, so x dot at 0 or dx by dt at 0. And those are, so we specify the initial conditions and then find the function of the dependent variable over the rest of the time. So the initial values lead to a particular path that is a function of time, so x of t. So a boundary value problem is an ordinary differential equation given with boundary conditions at different points. So this usually applies to static systems whose independent variable is position. So for example, the Euler-Bernoulli beam deflection equation is a boundary value problem. In this case, the boundary conditions of deflection, so y, as well as the rotation, so y prime or dy by dx, and the third and fourth derivatives of y are usually given at boundary points on the beam, which will then dictate the equilibrium deflection of the beam as a function of position y of x. So depending on the different boundary conditions of the beam, so if it's fixed at both ends or cantilever beam, we get a different solution to our boundary value problem.